This is video number 2 for 920. So if you're watching this first, go back and watch video number 1 because there's a lot of information there. I don't know if it's really useful, but there's a lot of information. All right, so we started that example at the very end of the first 15 minutes. And we found U1, V1, U2, and V2. And hopefully you are following this, remember? And now that we have everything, because we also have the pressure and we didn't interpolate for anything at all, now I can calculate work and I can calculate Q. All right, work with P delta V because it's quasi-equilibrium. And the first semester ever, I say this at the very beginning, so thank you, all right? And then we have Q is W plus delta U, and Q is in, work is out because of the sign convention, all right? The values themselves don't matter that much right now until we get to later on, like combining everything, all right? How do I use this value of Q, this value of W combined with another part of the problem to find out how efficient this cycle is and so on, okay? Now, it is shown there on a TV diagram. It doesn't say anything. I should add to it. But a PV diagram will look exactly the same right now, all right? Because it's going from saturated liquid to saturated vapor at constant temperature and constant pressure. All right, the very next page, the yellow one over here, okay? I did not rewrite it, but it's not wrong. I just changed some of the numbers, and that's why you see some red. After those examples that we went over, now we have yet to cover superheated vapor, compressed liquid, linear interpolation, quality, and longer problems. No homework, so ignore that part. Superheated vapor tables, it's A6 for water. It's other tables for other substances. Have not decided if we're going to cover other substances yet. Now, if you go to table A6, you will see that there are multiple smaller tables, right, within that table. And so in one page, I believe they have 6 or 9 tables per page, and each one corresponds to a different pressure. So make sure you take a look, okay? For a different pressure, you have temperature on the very first column. So if you know the pressure and the temperature, you can find any of the other properties, intensive properties that you need, that you have available there. Specific volume, internal energy per unit mass, specific enthalpy, specific entropy. All right, specific entropy, very useful also for second law later. Keep mentioning it. Told you guys, well, traumatized by the whole experience. So they're not that difficult to use because we don't have to determine what we have, like how we did for saturated tables. Now it's just trying to locate the pressure. Hopefully we have the pressure. Those are the easiest examples because we locate the small table corresponding to that pressure. We look for another property, and everything on that row corresponds to that state. An example is pressure 300 kilopascals, which is approximately 3 atmosphere, a little bit lower than that, and temperature 300 degrees Celsius, okay? Now, let's say that we're looking for the specific internal energy. Then we go to table A6, and we can retrieve it, 2807 kilojoules per kilogram. I used another table for this, so if you have something different, just please contact me, okay? Because I don't have the textbook now with me. Now, before we find the specific internal energy, we are supposed to go to table A4 or A5 and check what we have. Like at 300 kilopascals in table A5, we're supposed to check the temperature of saturation right next to it. If this one is higher, it means that we have superheated vapor. So we move on to table A6, okay? Then from A6, we can find any other properties that we need. Now there, I see another example. It says pressure 0.5 megapascals, specific volume. Can't see this. 0.61731 cubic meters per kilogram, apparently, and we need to find the temperature. So, not trying to make this unorganized, but I don't have my textbook as I mentioned, so I don't know what the temperature is, but please look that up, all right? 0.5 megapascals is 500 kilopascals, so the first thing that we're supposed to do is go to table A5, compare that specific volume over there to VF and VG. If it's greater than VG, which is what I suspect, if it's here, then we will have superheated vapor. If it's superheated vapor, we move on to table A6, okay? So you would have to go to 500 kilopascals or 0.5 megapascals in table A6 and locate that specific volume. If you can find that specific volume there, then everything else on that row corresponds to that state, okay? All right, so if you have any questions up to here, please send me an email or call or whatever you want, okay? The next part, compressed liquids. If you have your table A7 and you take a look at it, you'll see that it's very limited. Not only does it start at a really high pressure, but I think you only have one page in your textbook, and it's just really limited. And I think it jumps like 500 kilopascals or something like that from one smaller table to the other. So it's not very helpful for this class and for a lot of other classes. Instead of using those tables, now based on that diagram that I sent to you, that in reality, okay, VF doesn't depend that much on pressure, it depends more on temperature. When we have a liquid, instead of using a table, we'll use that approximation over there. That I always say it, and students always lose it on their notes and then they can't find it. We'll say that V is approximately VF. It doesn't say approximately there. There's approximately VF at the temperature. And same thing for a specific internal energy. They depend more on temperature than on pressure, okay? So an example there, if I have 1 bar and I have 25 degrees Celsius, so 1 bar is 100 kilopascals, then I determine, okay, again, I used another table, so that's why it says A2 or A3. I determine that it is a compressed liquid because at 100 kilopascals, that temperature over there is lower than my saturation temperature. Okay, so I have a compressed liquid. So the next thing that I do is find the specific volume, because that's what it's asking for, the saturated liquid value at the temperature. And it will be very close, all right, to the specific volume of that compressed liquid. Sorry, I got distracted. So the density doesn't change that much, right, when we have a liquid, and it depends mostly on temperature, not so much on pressure, okay? Now, over here, it says we may use A2 or A3, because again, this over here, I was using other set of tables, but in reality, is we may use A4 or A5 to determine that it is a compressed liquid. So I suggest, or like Brooks says, I invite you to take a look and prove that that is true, or check that that is true. That at 100 kilopascals, that T is lower than Psat, or at that T, that pressure is higher than Psat. All right, you can use either table. Once we determine it is a compressed liquid, we have to go to A4, okay? From A4, we see that it is 1.003 divided by 1,000 units for the specific volume. So when we see compressed liquids later on, we'll discuss this again, okay? Just from compressed liquids, I want you to know that we do an approximation instead of using tables, and that's the way you're going to keep doing it moving forward, okay? All right, last part, quality, okay? Let's see. What is quality? Quality is the mass of saturated vapor divided by total mass. Now, this only applies when we have a saturated mixture. So remember, when we have a saturated mixture, pressure and temperature depend on each other. And just by having those two values, it's not enough for us to say we have this state, okay? Even if we have quasi-equilibrium, okay? So this value of X will tell us how much of the mass, not the volume, how much of the mass is saturated vapor, right? How much of the total mass is saturated vapor. So half of the mass is saturated vapor, X is 0.5. This means that X is equal to 0 for saturated liquid. We would say this is a mixture with no vapor yet, all right? It's equal to 1 for saturated vapor, and it's in between 0 and 1 when we have a mixture of the two of them. It does not apply, so you should write this down if you are writing stuff down. I don't know if you are. It does not apply when we have compressed liquid does not apply when we have superheated vapor. People are tempted to say that X is 0 for compressed liquid and X is 1 for superheated vapor, especially the one for 0 for compressed liquid. The issue with this, they say, well, there's no saturated vapor, no? And using that reasoning, it could also be 0 for superheated vapor. But then when you go to work, even if you are in industrial engineering and you have to do this one day, then you write down on your code or the program that X is 0 is going to give you the saturated liquid values, okay? So equal to 0 for saturated liquid, equal to 1 for saturated vapor, in between 0 and 1 for mixture, doesn't apply for compressed liquid and superheated vapor, okay? Now, having X, all right, will help us to fix the state in the saturated mixture region. It is, all right, an intensive property, and it is independent of pressure and temperature, all right? This means that if I have pressure, X is not fixed, okay? Now, 2 examples over here. If I have the temperature of water 100 degrees Celsius and the quality is 0.5, what is the pressure, all right? Now, the pressure is 101.42 kilopascals, and that is from table A4, okay? Not A2. That says A2. Maybe I'll fix it before I send it, but just in case. What about if X is equal to 0.7? What do you think? Will it be higher than 101.42? What do you think? Hopefully you're thinking. It will be the same, all right? As long as the quality is in, as long as the quality is in between 0 and 1, the pressure will be the saturation pressure because that's telling you that it's in the saturation region. Very next example. Pressure 4 bar X equal to 1. What is the specific internal energy? So 4 bar is 400 kilopascals. I want you guys to get used to this other unit over here. And X equal to 1, quality is telling me that all of the mass of my mixture is saturated vapor. That means that U is equal to UG, and you find this on your table A5, okay? So you go to your table A5, all the values that have the subscript G are the values corresponding to this state. VG, UG, HG, and SG for later, okay? Now, I don't want this to last more than 15 minutes, so let's finish with this derivation over here. Now, since X is mg divided by mf plus mg, where mg I use to represent the mass of saturated vapor, mf the mass of saturated liquid. We want to use this to develop an expression for the specific volume of my overall system, okay? Now, we cannot add the intensive properties. We talked about that before, okay? I cannot add the pressure acting on this section of the phone plus the pressure acting on this section of the phone and say the total pressure is this plus this. No, all right? However, I can add the extensive properties. That next line that you see over there is the actual, total volume, all right? The total volume. Make sure you understand that. It's going to be in one of your tests. Next test, not take home, by the way. Sorry. Yeah, so I can add the volume. I cannot add the specific volume. The volume is mass times specific volume. Make sure you do that by hand one time, okay? So that means that if I have mass times specific volume for each of those terms, I can solve for my overall specific volume as a function of this value of X, as a function of VF, and as a function of VG, all right? Now, the examples, I'm going to do them next time. When we come back on Monday, we're going to... Oh, we have so much left. It's fine. We're going to go over this again. Quality, all right? I might have like an extra credit... Okay, I combine everything there. An extra credit quiz or something like that on this. Like how to go from quality and my equation where I can add volume to get to specific volume. I want you guys to practice that just once, okay? Then when you come back, we'll see examples. And thank you for watching if you're watching. And if you're not, then, well, you won't see this part anyway. All right. Have a great weekend.